In this presentation, I'm going to present some of the work we did on the load rating of movable bridge using BrR. When we talk about the movable bridge, we are talking about the bridges as shown on the screen right now. This type of bridges, there were many built in the 1950s, 60s, 70s, and many of them are already in service for 50 years or even more. So it's very important for us to load those bridges because the code has changed, condition has changed. So we have to load this to make sure the bridges are safe. But the thing is, for movable bridges, there are always some special consideration that we always need to take into consideration that there are some special tricks to load this bridge. Otherwise, if you load it like a normal bridge, you almost guarantee that you will make mistakes. So in this presentation, I'll just show how we load those bridges using BrR. This is what is going to cover in this presentation. First of all, we are going to talk about the challenges or any special considerations that when we rate movable bridges. Second of all, we are talking about the solutions, how we are going to do this using Ashto BrR. At the end, we are going to look at one case study that we load rate movable bridge. We use load test and also the bridge rating. We're mainly going to focus on how are we incorporate the load test result into the BrR. So this is a movable bridge or specifically a swing bridge. And as you can see here, this bridge usually have like a pivot in the middle and have two supports at the end. And the swing on the pivot can swing open. Then when they come back, they put the wedge underneath. And so the wedge, the purpose of this wedge is make sure this deck is going to be level with the approach stance. The challenge of load rating this bridge, first of all, the first issue is that they have different supports on the dead load and the live load. I'll explain a little bit more. First of all, let's look at live load. Live load, I think there's no question. So whenever we model this bridge, we put a support at two ends and also at the pivot in the middle. Because once the bridge swing back to this position and you put the wedges in there, it can support all the live load. It's like two span continuous bridge. It's more like that. But the question is about the dead load. In dead load, can we still just use those three supports? The answer is no. Okay. Just imagine this. You have the bridge swing open and all the load is applying to this pivot in the middle. When the swing back, yes, we put these wedges in, but those dead load was not applied to this two span continuous bridge from the beginning. At the very beginning, it's only supported in the middle. When you swing back, this is just an additional wedge force at the end. If you just model this as a two span continuous from the beginning and you look at the dead load, it's going to be totally different. So the correct way is just when you consider dead load, just put one support in the middle, plus add two wedge force at the end. One support plus two wedge force. It's not three support. This is the correct way to load rate the swing bridge. I'll show the difference later. I'll show the difference later. That was the first issue. The second issue is we have two cases of dead load. That's mainly due to this wedge force. Because wedge force, the amount of wedge force, many times we don't know how much is that. We know that when you swing back, you put this wedge on, it's more like add a deformation over there. But how much force will caused by this deformation, you don't really know. And this force many times actually change. It's change it's due to the stiffness of this bridge. Sometimes, for example, if there's section loss or even some temperature change, it will change the stiffness of the truss. So for the same wedge deformation here may cause different forces. We don't know how much is that. And many times in design or the rating, we usually consider a minimum force and a maximum force. And we need to consider both cases and find whichever control. So usually, many times we consider the wedge force equal to 0 as the minimum, and we need to consider maximum wedge force. Let's look at one example to show what's the difference between this case 1 that you have wedge force equal to 0, case 2 for this bridge, you have the wedge force is 60 kips, and also for the both cases, I'm going to compare to the case that with the 3 supports applied from the very beginning and basically treat this bridge as a 2-span continuous. I'm going to compare that the result. Just a little bit briefly look at this bridge. This is the arch-shaped movable bridge. You can see those are the top chord members. At the bottom, these are the bottom chord members, and you also have vertical members and the diagonal members. And we are mainly going to look at the forces in the top chord members and the bottom chord members. This is compare the forces in the top chord members. When we say case 1 is this red one, that means the one without the wedge force. Wedge force equal to 0. And this is plot along the length of the bridge. So you remember that when we do this bridge, when we do this case, we only put one support in the middle. So this bridge is basically you have one bridge in the middle and the cantilever on each side. So when we talk about the top chord member, they are all in tension with the maximum tension in the middle of the bridge. So you can see here, this is case 1 planes. When I call it planes, that means this force we pull out directly from the planes. Of course, we also did our own calculation and verified this force, and our result exactly matched the design. So case 1 without the wedge force, that's the force in the top chord member. Case 2 with 60 kips wedge force on each side. You apply the wedge force on each side, and this is your load on each member. And at the bottom, the blue line, this is when you apply 3 supports at the beginning. You can see how much is the difference in terms of force. So if we just treat this movable bridge as a normal bridge, just apply those 3 supports at the beginning. You can see the difference. Actually, I have seen people did it in that way. And unfortunately, this is incorrect. And also, what makes it worse is that this is actually on the unconservative side. Look at how much we underestimate the dead load. The same thing for the bottom chord members. Bottom chord members, again, this red line right here is case 1 without the wedge force. At the bottom chord member, they are on the compression because we only have a cantilever only have one support in the middle, 2 cantilever outside. So the bottom chord is in compression, so we put in negative value. The maximum compression is at the members that are close to the middle, close to the pivot. And this yellow line is when we case 2, that we consider the wedge force. And again, blue line, this when we put all 3 supports, treated as a normal bridge from the beginning. And again, you can see how big is the difference. So the main challenge is here. First of all, live load, we have 3 supports. No problem, no question on that. Dead load, we only have 1 support. And unfortunately, in BrR, you cannot really switch between this. You cannot set different boundary conditions, set different supports in the model for the dead load and the live load. And also another challenge is how can we consider those 2 dead load cases? Because in BrR, there is only one of the case, only one dead load case we use in the load rating. Okay. So if this is a one-time job, the first impression you see, we can always load rate this bridge. They say, okay, I'm going to just build 2 models. 1 model for dead load, 1 model for live load, and I'm going to just pull out the result and the load rate in the spreadsheet. Okay, that's a solution. But the thing is, if this is a one-time job, that's okay. We can do it. But our client, they need a model that they can use in the future. Because the DOT, they need a model to assign permit often. Many times they use BrR to assign permit for those heavy vehicles, and they do it every day. And you cannot imagine that they need to extract the data, dead load, live load separate from the model every day, and try to put in a separate Excel or Mathscat to do the rating. So the challenge here is how are we going to build a model in bridge rating can take care of those 2 issues, and this model can be used in the future. Okay, so this here is a solution. First of all, for different supports under dead load and live load. Again, remember dead load, we only have 1 support in the middle. Live load, we have 3 supports. We have no option. First of all, we have no option. We have to assume supports at cantilever ends and for the live load. In other words, in bridge rating, we have to do the model with 3 supports. That's the only way we can do to handle the live load. The live load is always the difficult part because live load, you need to consider how the truck positions, different trucks. We have to rely on the software to calculate live load for us. Now, of course, if we build this model as a live load, for live load with the 3 supports, then how can we account for the dead load? How can we handle the dead load in the correct way? The solution is to override the dead load for the truss members. Maybe if you have followed the discussion, you may come up with a question like, okay, you override the dead loads, but for which cases? Remember, we have 2 cases, case 1 and case 2. And which are we going to use? That's for the 2 dead load cases. So most specifically, we need to override the dead loads for truss members with the controlling cases. Different members, they may controlling by different case. Some member may control by case 1. Some member may control by case 2. We need to find the controlling case and override the dead load on that member. This can, according to experience, usually the members close to the pivot. That's the ones always controlled by case 1. Some members close to the end, the start and the end, and especially some diagonal members, they may control by case 2. Many times you can do that by experience, or if you're not sure, the worst case, you just run case 1 and case 2, then compare the result, find which member is controlled by case 1, which member is controlled by case 2, then override the dead load for that trust member. And here is how you override the dead loads for the trust members. You can see we all know that in trust, in BrR, when you load the trust bridges, this is the input. You have this kind of like a text file that you need to manually define the member properties or everything. And here, they also have a very detailed manual, like on how to use those commands. Here they have one command. It's called override the capacity, and they have 3 values after that. The first one is the tension capacity. Second one is compression capacity, and the third one is the dead load axial force. So in order to override that dead load, well, all you do is go to here. You see define the member. Then the first one is tension capacity. We don't want to touch that. Put a pound key. And the second one, compression capacity. We put a pound key. And the third one, that's the dead load. And we just override with the dead load in there. This way, live load is correct because we build the model use 3 supports. We treat this bridge as 2-span continuous, kind of like. And then dead load, we calculate using other software that manually override the result here. So this way, this model is the correct model. And the DOT, they can use this model in any future analysis. Now we look at the case that we did on a movable bridge, and we actually use BrR as an analysis engine, and we also did a load test, and then we apply this load test result back to BrR, and so we just calibrated the BrR result, and so more represent the actual condition of the bridge. As you can see here, this is the bridge. They have this swing spans in the middle. Approach spans, they have those steel girders, and also at the very end, they have some short. Those are the concrete slab spans. This shows a picture of the swing span. On the left is this bridge is just about to swing. This is a swing span, and this is when the bridge swing open. We did a load test with the instrumentation. This is not the main purpose of this presentation. I'll just go quick. You can see there, this is the end flow beam. In the middle flow beam, we did the gauges that we applied the gauge at the top flange, bottom flange, and then connected to this. This is the wireless nodes, and they can transmit the data to the computer. And those are the steel girders. So you can see those are the gauges that we put at the bottom. This is the truss, the gauges we put on the truss member. And those are the gauges we put on the approach slab spans. The installation of the slab span was very easy because you can work from the ground. And those ones actually was a pain to install because you have to work on the boat. Because this bridge, there was no detour on this bridge, and they cannot close the bridge. So we have to work everything from the bottom, from the boat, and this is pretty high. And then we did a load test. We bought the trucks, the 2 heavy trucks. We put them all in different locations, and one truck loaded, 2 trucks loaded side by side, and we put at different locations to maximum the nodes on the approach spans, the girders, and the floor beams, or the truss members, and we collected the information for the analysis. Here shows some of the members that we did the analysis on. There are many on the swing spans. Oh, sorry. Those shows the deficiency members. For the swing spans, We have flow bin A, which is the end flow bin C, intermediate flow bin, and the truss members. And for steel I-beam spans, the exterior beam, interior beam, and also the concrete slab spans. You can see here the load rating factors for legal vehicles are all below 1. Here we are only interested in legal vehicles because we usually just post the bridge on based on the legal ratings. You can see here all those load ratings are below 1. So we came back, we started the analysis. First of all, we did the model. We built a model in Ashton. This is the truss, and this is the cross section of the truss span. This is the approach span. Of course, we also did a finite element model. This is the truss span. For the finite element model, everything was built using the shear element or plate element. Even the girder flow beams, for example, I-shaped flow beam, we didn't just use a simple beam element. We actually used 3 plate element, one for the top flange, one for the bottom flange, one for the web. This is the approach slab span with 4 steel beams, and this one is the slab stance, approach slab stance. And you can notice that on the side they have this, those are the raised sidewalk, and this actually add quite some stiffness on it. So we have to model this sidewalk. And also for the applied load, we cannot apply the concentrated load. We have to consider the area, 10 by 20, the footprint of these tiles. Then we compared the test result from the truss members. You can see here, those are the truss members that we test, and those are the gauge numbers. And this is what, in terms of macro strain, how much macro strain we measured at the field. This is what I calculated from the finite element analysis, and this is what I calculated using the Ashton equations. You can see here what we measure at the field was much less than the finite element model and the BrR. The same thing for the flow bin A. Flow bin A is the end flow bin. This orange line right here, that's the Ashton result from BrR. This yellow line is finite element model, and this green line is what we measured at the field. This actually is very typical. Many times, the Ashton equations always have the highest value because it's more conservative, and those equations are developed for all different bridges. So many times those equations are more like an envelope of different bridges in terms of the load distribution. Finite element is usually more close to the actual condition, and the field test is usually have the lowest measurement. Same thing for the flow bin C, which is the intermediate flow bin. Again, maximum is the BrR result from the Ashton equation, and then finite element and the field test. This is the result for the exterior bin. Exterior bin, you can see there's a large difference between the field test and the Ashton code. I think the main reason is because the barrier. The barrier add quite some stiffness to the exterior bin, but that's usually not taken into consideration when you do the structural analysis. Then this for the interior bin approach span, you can see again the same trends. We also did move the truck transversely and plot all the data, and this data can be used to calculate the actual distribution factor, level distribution factor on the steel beams. Then after we finish all the result, the question is how are we going to incorporate this result to the bridge rating? Again, the challenge is really, if it's a one-time job, we can always do it separately and send the result to the DOT. But the thing is they need a model can use in the future analysis. So whatever we test, we have to incorporate this result into bridge rating. Of course, first of all, we need to calculate the adjustment factors according to the manual for bridge evaluation. Basically, based on your analysis result, the manual for bridge evaluation, they have a set of equations that you can basically apply adjustment factors to the bridge that can reduce the live load on the girders or truss members or whatever member you're interested in. We are not going to talk about it in details, like how to calculate those. Then, first of all, how are we going to incorporate that to the truss member and the steel beams? Those are very easy because we can just simply change the live load distribution factors for those member. Again, those adjust factors are only for live load. Okay, those are only for live load. So we can simply just update the live load distribution factor for the truss members and the steel members. Then for the concrete slabs, it's a little bit tricky because during the test, we can find that the boundary condition actually was not simply supported. Even the concrete slabs, they were designed as simply supported. But because their dowel bars connect the concrete slab to the top of the cap, they actually provide some fixity. It's actually between simply supported and fixed. In that case, but the good thing is that in BrR, you can adjust the boundary condition. You can even apply a spring, torsional spring at the end to represent the actual stiffness as the actual condition of the actual boundary condition. This is very convenient functions in BrR. Then for the floor beams, there's no such thing as live load distribution factor. So the only options we had was to set a different set of live load factors only for those floor beams and apply those to floor beams. Basically, we reduce the live load factors for the floor beams. As you can see here, the bridge rating, the actual bridge rating cannot handle the movable bridge directly, which I understand because no software can cover 100% every type of bridges. It's just not the way. But the one good thing I really like bridge rating is that they have all the functions, options that you have the control. It's like have this flexibility that you can trick the program. That you can, even the program does not directly support those functions, but since you have the control, that you can always adjust this, play with it, and meet what you want to do. So that's after we did everything, and that's the compare of the rating before and after the load test, and also we apply all these changes to the new bridge rating model. You can see here all the load ratings, they were improved, especially the floor beams, intermediate floor beams, also approach I-beam span, steel I-beam span, and approach slab spans. Right now they all have load rating factors above 1. Floor beam A that's the end of floor beam. It's very low. It's because according to the code, right now the impact factor for the end of floor beam in movable bridge only, impact factor is 1.66 instead of 1.33 for the other bridges. Basically double the impact. So 0.66 versus 0.33, you have a very large impact. That's why you have this is a new requirement. All the older bridges, I guess, they didn't design for this high impact factor. So that's why they have very low rating. And also the trust number, it was 0.64. Now it's almost 0.9. So it's also a big increase. Those two members that are currently, we are doing some strengthening plans for those members, and hopefully after the repair, we can remove the posting of this bridge. Also, because of all this analysis, at least we don't have to, we can avoid some unnecessary strengthening on the other members, like the intermediate floor beam and or the approach spans. I want to take this chance to thank Louisiana DOTD for all their support. Also, all the technical discussions during this project. We couldn't do it without their help.